Very good evening, students.
Good evening. Good evening.
So let us start the discussion without wasting any time. Last class we have been discussing about the type of reagents, right? In the general organic chemistry, we have to understand what type of bond cleavages occurs, homolytic cleavage and heterolytic cleavage. Homolytic cleavage means the electronegative difference is going to be very less, and the bond pair of electrons are going to be shared, generating free radicals. Heterolytic cleavage means you will be generating ions, and the electronegative difference is going to be high. So in that perspective, after the bond cleavages, we have seen about reagents. Reagents are two types: electrophiles and nucleophiles. Electrophiles are electron deficient species which have a tendency to accept the electrons. The species which are having a tendency to accept an electron, they are said to be electrophiles. The first type of species which can behave as electrophiles are positively charged with incomplete octet. The positively charged species with incomplete octet, they can act as electrophiles, like all these examples. And neutral molecules with an incomplete valence shell, they can also act as electrophiles. Right? These are the two cases where we have which we have studied already in the last class. Like the species must have a tendency to accept the electron. Then only it is called as an electrophile. So third kind of category is neutral with complete but expandable valence shell. The neutral molecules with complete but expandable valence shell, like PCl5, SnCl4. PCl5, if you try to write the electronic configuration of phosphorus, it will be 1s2, 2s2, 2p6, 3s2, 3p3. But 3d is vacant. Yes or no? You can write in the first excited state, you can write 3s1, 3px1, 3py1, 3pz1. In the 3d, you can have 5 d orbitals, where 1 d orbital can be filling the electron. Remaining 4 d orbitals of 3d subshell, they are vacant. So actually, the electrons can excite due to the presence of vacant d orbitals, it can still accept the electrons. That means PCl5, SnCl4, due to the presence of vacant d orbitals, they can accept the electron, and thus they are going to be behaving as respective electrophiles, electron accepting species. Compounds containing polar pi bonds can also act as electrophiles, like CO2, SO3, COCl2, RC double bond H. If you think of RC double bond H, RC double bond H is an aldehyde group. The C double bond O, the pi electron density is moving towards oxygen, generating partial negative one oxygen and partial positive one carbon. So whenever we have a nucleophile, the nucleophile has a tendency to attack this particular electrophilic carbon or not. RC double bond H is a carbon double bond oxygen is there, where the pi electron density is moving towards oxygen. Since the pi electron density is moving towards oxygen, why? Because oxygen is more electronegative. Because of that movement, this carbon has some electrophilic nature, so it can be attacked by any nucleophile. Not only RC double bond H, wherever you have polar pi bond, compounds containing polar pi bonds can act as electrophiles. Here existing bond or pi bonds needs to be broken. The pi electron density is going to be donated to oxygen as soon as the nucleophile attacks. Earlier we have partial positive one carbon, partial negative one oxygen. But as soon as the nucleophile attacks, this C double bond of pi electron density that will be given to the oxygen atom. So we'll generate what? We'll generate our carbon's positive charge is going to be now neutralized because it forms a new bond with nucleophile, and the carbon will now have a single bond with oxygen, but oxygen will have a negative charge because the pi electron density has been given to oxygen atom. The pi electron density is given to oxygen, so oxygen will be posting a negative charge. Right, students?
Yes, sir.
So these are all the cases of electrophiles. Electrophiles are those species which are positively charged with incomplete valence shell, less than 8 electrons, that is neutral molecules with incomplete valence shell, complete valence but complete octet but expandable valence shell, that is presence of vacant orbitals, and also compounds containing polar pi bonds. All these are coming under the category of electrophiles. Next, let us go with the nucleophilic reagents or nucleophiles. Electrophiles are electron accepting. Nucleophiles are nucleus loving or electron donating. So we can say a reagent that brings an electron pair to the reactive site, that is said to be nucleophile. A reagent that brings an electron pair to the reactive site. So there was a reactive site like R, C double bond H, the same example which you have taken. The pi electron density moving towards oxygen, partial negative on oxygen, partial positive on carbon. There is a species like Nu minus which will bring the electron density toward the carbon. This species which can bring the electron density, this is said to be nucleophile. This is said to be nucleophile, is electron rich. Electron rich species. Yes or no? Or electron rich species which have a tendency to share the electron, that is said to be nucleophile. First point, negatively charged species, they can act as nucleophiles like H minus, OH minus, OR minus, Cn minus, X minus, R minus, R C double bond O minus, NH2 minus, SH minus. Neutral containing lone pair. Neutral molecules containing lone pair with complete octet. Yes or no? Neutral containing lone pair with a complete octet. Write down that point. Neutral containing lone pair with a complete octet like H2O. If you look at H2O, hydrogen is connected to two oxygen atoms. Oxygen has two lone pairs of electrons. Oxygen has two lone pairs, 4 electrons and 2 bonds. So in total 4 plus 4, 8 electrons are there around oxygen atom. So oxygen has a 8 electrons, octet is satisfied. So it has a lone pair. Lone pair is not involved in any bonding. So now that lone pair of electron present on oxygen, that can be used in the attack. So that can be acting as a nucleophile. Neutral molecules containing lone pair of electrons, that can act as a nucleophile. H2O, ROH, ROR, NH3, RNH2, R3N, PHOH, all these can act as nucleophiles. CCl2 can act as a nucleophile, CCl2. CCl2, dichlorocarbene.
Yes, sir.
Yes or no? Ayushi says, because it has a lone pair of
Yes, sir.
electron. Can it act as a nucleophile? It cannot act as a nucleophile. Why?
No,
Due to
Because it
back
has
bonding.
only 6 electrons around the
6
carbon. So it has a tendency to accept the electron pair to get the octet electronic configuration. So it will act as a strong electrophile. Strong electrophile, as it has a tendency to accept electrons to get octet electronic configuration. And where do we have the CCl2 reactions? Any reaction you can remember where CCl2 is there as the intermediate?
Reimer-Teimer.
Any other reactions? Carboylamine reaction, can we have CCl2 as an intermediate? Okay, we'll discuss all those reactions. Reimer-Teimer is the right answer. But we have different reactions where CCl2 dichlorocarbene is present as the intermediate. And we'll be looking at, in that reaction, you can easily observe it is accepting the electrons. The CCl2 is actually accepting the electrons on the pi electron density of your benzene ring. Yes or no? So that means it is acting as a electrophile, not a nucleophile. And pi electron donors like alkenes, benzene. Benzene will undergo electrophilic substitution reactions. Alkenes will undergo electrophilic addition reactions, if you remember. Yes or no? Alkenes and alkynes will undergo electrophilic substitution. Electrophilic addition. Substitution will be undergone by benzene. Alkenes and alkynes will undergo electrophilic addition reactions. And benzene will undergo electrophilic substitution. Yes or no? Pi electron donors, alkene, alkyne, benzene. RMGX, LaLH4, NaBH4, they are also acting as nucleophile because RMGX organometallic compound known as Grignard agent. The partial negative will be developed on carbon, partial positive will be developed on magnesium, because carbon is going to be more electronegative when compared to magnesium. LaLH4 and NaBH4 produce hydride ion. That hydride ion is also acting as a nucleophile. So nucleophiles are negatively charged species or species which contain lone pair of electron with complete octet, or pi electron donors like alkene, alkane, benzene, organometallic like NGX, LaLH4 and NaBH4, that is reducing agents. These are all species can behave as nucleophiles. This is a broad introduction. So let us proceed. Ambident nucleophiles means nucleophiles which have more than one electron in its center. Any examples of ambident nucleophiles? Nucleophiles which have more than one electron in its center.
Cyanide.
Example, yeah, cyanide, NO2, NH2OH, where lone pair of electrons are present on nitrogen as well as oxygen. NH2, NH2, hydrogen, where lone pair of electrons are present on two nitrogen atoms. So all these are the example. In NO2, we can have lone pair of electron nitrogen or negative charge on oxygen. Both can donate the electron pair. Cyanide, carbon can donate the negative charge, or nitrogen can also donate the lone pair. So all these are the examples of ambident nucleophiles where you can have two possible attacks at the same time. And amphiphile means that compound which can behave both as an electrophile as well as a nucleophile. You can take a simple example of RC double bond H. This carbon is going to have partial positive charge. The oxygen will have partial negative because of the movement of pi electron density. So this carbon is going to be acting as an electrophilic carbon. Oxygen acts as a nucleophilic oxygen. So this species will act as both electrophile and nucleophile. Cyanide will also have tendency to act as both electrophile and nucleophile. So there are some compounds or species which can act as both electrophiles and nucleophiles. They are said to be ambiphiles. Ambident nucleophiles are those nucleophiles where we have more than one electron in its centers or nucleophilic centers. Yes or no? Ambident nucleophiles are those nucleophiles which have more than one electron in its center. And we can have different other nucleophiles like negatively charged species or species with complete octet, pi electron donors, and also organometallic like Grignard reagents and LaLH4 and NaBH4. Let us look at the next point, reaction intermediate. So any species formed during the bond breaking in the reaction, that is known as reaction intermediate. Like we have R1, R2, R3, three alkyl groups connected to carbon, and carbon is also connected to some Z group. So we can have carbocation, carbanion as well as free radical form under different sets of cleavages. Yes or no? This is carbocation. This is a free radical, and this is carbanion. Carbanion, where the negative charge is present on that particular carbon. So let us look at these intermediates at the basic level. Then upon introduction of electronic effects, we'll study the stabilities of all the intermediates as well. Carbocation and carbonium ion. So if you look at this particular carbon, it is having how many electrons around itself? This carbocation or carbonium ion has only 6 electrons around itself. So it has a tendency to accept the electron pair. So it is going to act as an electrophile. It is acting as an electrophile. It is having only 6 electrons around itself. So it will be having only sp2 hybridization, trigonal planar. Yes or no? It is obtained by heterolytic fission. Hybridization is sp2, trigonal planar. Valence shell has 6 electrons. Octet is incomplete, so it has a tendency to accept electrons. So that is why it is acting also as electrophile. And it is a Lewis acid because it has a tendency to accept electrophile. It is diamagnetic in nature because there is no unpaired electron. It is going to be diamagnetic in nature because there is no unpaired electron. All these points clear or not, students?
Yes, sir.
Heterolytic fission has to be done. sp2 is a hybridization. Planarity, sp2 hybridization means trigonal planar. Valence shell has only 6 electrons, so octet incomplete. So it is having a tendency to accept electrons. So electrophile, Lewis acids. Lewis acids are electron accepting species, and it is going to be diamagnetic in nature. Carbon free radical. How is carbon free radical obtained? So
Homolytic fission.
Yeah, homolytic fission. What is the hybridization? Carbon free radical CH3 dot means it is an odd electron. Odd electron species. What are the conditions I have told you? When the odd electron is going to be involved in the hybridization?
When the side atoms are more electronegative than.
When the side atoms are less electronegative when compared to the central atom, then no involvement of odd electron in the hybridization. If the side atoms are more electronegative, then the odd electron will involve in the hybridization. So CH3 dot So odd electron will not involve in hybridization. So sp2 hybridization. Trigonal planar again. Valence shell 7 electrons. Octet incomplete. So it is also have a tendency to accept an electron. So electrophile. It is paramagnetic in nature because of the presence of unpaired electron. It is a paramagnetic in nature because of presence of unpaired electron. Everything is going to be clear with respect to carbon free radical also. Same positions. Carbon ion means we have how many electrons? 8 electrons are present around the carbon. It is obtained by again heterolytic cleavage. What is the hybridization? Hybridization is going to be sp3 hybridization, but we have lone pair of electrons on one of the vertex of tetrahedron. sp3 means you should have what should be the minimum repulsion state? Tetrahedral shape. Yes or no? But one of the vertex of the tetrahedron that is now having a lone pair of electron. Because of that, the shape will be now trigonal pyramidal, like ammonia, similar to ammonia. Valence shell has 8 electrons because 3 electrons are in the bonds and 2 more electrons on carbon. Octet is going to be complete. It is acting as a nucleophile because octet complete and presence of lone pair of electron that will now act as a nucleophile, and it is a Lewis base similar to ammonia. Okay, similar to NH3. It is CH3 minus. You can compare that similar to ammonia because the CH3 minus has an 2 electrons extra with a negative charge. That negatively charged carbon is now going to be attacking the any other electrophilic centers, forming respective carbon-carbon bonds. Right, students? It is also diamagnetic in nature because there is no unpaired electron. If you have an unpaired electron, then only it is said to be paramagnetic in nature. Is that clear so far?
Yes.
Yes,
Yes,
right.
sir.
So carbenes is a neutral carbon species in which carbon atom is bonded to 2 monovalent atoms or groups and carries 2 non-bound electrons, like CH2 with a lone pair of electron carbon. Like 2 CH bonds and 1 lone pair will be present on the carbon atom. So around carbon you have 6 electrons. 6 electrons in the outermost shell. 4 electrons are bonded and 2 electrons are non-bonded. It behaves like an electrophile. It behaves like an electrophile because to complete its octet, it is not going to behave as a nucleophile, although it have a lone pair of electron, because it has only 6 electrons around itself. It is electron deficient and it has a tendency to accept the electrons, so it behaves as an electrophile. It is neutral in nature, CH2 with a lone pair of electron carbon. It is neutral species, but it has a tendency to behave as an electrophile. We have this carbene also classified into 2 types: singlet carbene, triplet carbene. We'll discuss that when we look at specific examples. In that particular concept, we'll discuss what is singlet carbene, what is triplet carbene, where the back bonding is stronger and where it is weaker. All those concepts also we'll discuss. Right? So then comes the electronic effect, students. Electronic effects start with first one, inductive effect, mesomeric effect, hyperconjugation, electromeric effect. Inductive effect, mesomeric effect, hyperconjugation effect, and electromeric effect. We'll start with one by one and understand all the electronic effects and their application. These are very, very important to apply, to understand and apply them to reactions. We have to apply them properly to different sets of reactions. That is why these concepts are very, very important. Inductive effect, mesomeric effect, hyperconjugation, electromeric effect. So inductive effect, can anyone say what is inductive effect?
Donation of electron density up to 3 carbons.
Why the donation happening? Because of electronegative difference. Okay. Polarization of a sigma bond caused by the polarization of adjacent sigma bond is referred as inductive effect. This effect is passed on the subsequent bonds also, but this effect decreases rapidly as the number of intervening bonds increases and becomes vanishingly small after 3 bonds or partial displacement of sigma bond electrons towards more electronegative atom is called inductive effect. That means you consider the system carbon, 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 carbon connected to some halogen atom like X. Carbon, 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 carbons. The carbon atom is connected to halogen atom. The carbon halogen bond will have 2 electrons. The shared electrons present between carbon and halogen, they are moving towards halogen, generating partial negative on halogen and partial positive on the carbon. I have just taken halogen because it is more electronegative. Because of the presence of partial positive charge on this particular carbon, can I say this carbon-carbon electron density will be moving? Obviously, because electrons are negatively charged, they are attracted towards positively charged centers. Carbon-carbon electron density will move, generating delta plus plus on this particular carbon. But this delta plus plus is less when compared to delta plus because it is a polarity or polarization of adjacent bond. It is a polarity developed on the real bond due to electronegative difference. These two carbons has no electronegative difference. Only thing is movement is happening because of this partial positive charge. Again, subsequent movement happens. So delta plus plus plus. After this bond, the polarization is almost nullified or is almost zero. So what is this? Partial displacement of sigma electron. The sigma electron density is actually moving in the direction of more electronegative atom. This is nothing but your inductive effect. Inductive effect of hydrogen is assumed to be zero. What do you mean by that? That means in the CH bond, whatever the electrons are present, the movement of electrons in CH bond was assumed to be zero. That means that CH bond is considered as a non-polar bond. So hydrogen is not either electron donating or electron withdrawing. Hydrogen is taken as a reference atom and inductive effect of that hydrogen is taken as zero. It arises due to difference in electronegativity. So based on difference in electronegativity only, the carbon halogen bond, the whatever the electrons are there, they are moving. Is that clear? Is everything clear so far?
Yes.
Yes, right. So CH3, CH2, CH2, CH2H. Now I have replaced the hydrogen with a atom Y as well as I have replaced with an atom Z. So Y has more electron withdrawing power than hydrogen. That means it is withdrawing the electron density. That means Y is an electron withdrawing group now. Electron withdrawing groups are minus I groups. Electron withdrawing groups are minus, like there are two types of groups. One can withdraw the electron density, one can donate the electron density. If a Z has more electron donating power than hydrogen, then Z is electron donating, Y is electron withdrawing. Electron donating groups are plus I groups, electron withdrawing groups are minus I groups. Everyone got these points or not? Electron donating groups are plus I groups, electron withdrawing groups are minus I groups. Inductive effect is distance dependent because the carbon or the carbon halogen sigma bond electrons, they were actually moving, developing polarity. So if the carbon bonds are increased, so obviously distance is going to be increased. So inductive effect will be distance dependent. It will be depending upon the distance. It decreases with distance and it is effective up to 3 carbon atoms. It decreases with the distance. With the distance, what is going to happening? The effect will be decreasing, and after 3 carbon atoms, there won't be any effect of inductive effect. That is no polarity is going to be developed greatly. Inductive effect is a permanent effect because the polarization is complete. Because polarization present throughout, polarization of sigma electrons. Sigma electrons is permanent because the bond is present. Okay, polarization of sigma electrons is permanent. Because of that, we can say inductive effect is a permanent effect. All these points clear? There are two types of groups, electron withdrawing groups or electron donating groups. This electron withdrawing or electron donating, this is completely based on electronegative difference. If electron withdrawing is happening by electronegative difference, that is said to be minus I groups. If electron donation is happening, then that is said to be plus I groups. Right? So plus I effect showing groups or atoms. Try to think of this as NH minus O minus C double bond O minus. NH minus, O minus, C double bond O minus. All these are plus I groups or minus I groups. Already the heading has been given. They were all plus I groups, which will have greater inductive effect, greater electron withdrawing tendency.
NH.
NH
Why?
due to low electronegativity. Then oxygen.
NH minus, like this is the scenario, CH3, CH2, NH minus. So it is electron donating group or electron withdrawing group? Electron donating group. So yeah, NH has a nitrogen. NH minus means nitrogen has a negative charge. The negative charge is present on less electronegative nitrogen atom. So less electronegative atom cannot withhold the electron density or negative charge greatly, so it has a tendency to donate. So NH minus nitrogen is less electronegative. Less electronegative atom can donate the negative charge or electrons easily. More electronegative atom cannot donate easily. So NH minus is having greater plus I effect than O minus. O minus and C double bond O minus you compare. If carbon is connected to C double bond O minus, C double bond O minus, the negative charge on oxygen is actually in resonance with C double bond O. So net donation is actually decreased. So NH minus will have greater than O minus, then C double bond O minus. This is the order of plus I effect for these species. Second set of species I'll give. Carbon connected to CH3, CH3, CH3. Carbon connected to 2 methyls, CH2, 1 CH3 and CH3. So what is the order, effect now? Plus I effect is directly proportional to number of carbon atoms. Like all methyls are electron donating groups. So ultimately this carbon will be a better electron donating group. So it will have greater inductive effect. Then you will have this one. Then you will have CH2, CH3. Then you will have methyl group. Yes or no? That means CH3 taken thrice will have greater effect than CH3 taken twice, than CH2, CH3, than CH3. Because more number of alkyl groups, more is the electron donation. Yes or no? Like for the same person, if all are giving the money, if all are donating their money to the same person, obviously that person's electron density or money is going to be increased. Same thing, if all the methyl groups are donating to the same carbon atom at a time, more number of carbon atoms, more number of donation, more will be the electron density. So that is a better electron donation group. Compare here third case, CH, CH3, CH3, CH2, CH2, CH3, CH2, CH3. This is one group. This is second group. CH2, CH2, CH3. This is third group. CH2, CH3. Which will have greater? To this particular carbon, 2 methyls are donating simultaneously. To this particular carbon, this carbon is donating. Again, that is donated further. To this particular carbon, only methyl is donating. Can I say in the first 2 methyls are donating simultaneously from the two sides? Like it will be having greater charge. Yes or no? Like I am giving 100 rupees to my friend and asking my friend to give, pass on to the next friend. But what my friend is doing is he will just withhold some 20 rupees and he will give only 80. If I directly give 100 rupees to the last person, the last person gets 100 rupees directly from me. But if I give to it my friend and my friend uses some 20 rupees and gives 80 rupees only, in that case some loss in electron density happened. So look at the ethyl case and 2 methyls directly connected. So electron donation happening from 2 methyls directly. So here the electron density is greatly. First the electron donation has to happen with respect to CH2. Then due to the polarity developed here, again electron density is happening. So CH2, CH3 will have less electron donation tendency when compared to your 2 methyls connected directly. So that will have greater inductive effect. And only 1 methyl means that will be less when compared to ethyl group. Is that clear?
Yes, sir.
Yes.
These are simple, very simple basic concepts. Like more the number of alkyl groups, more is the electron donation tendency. Try to compare here. Tritium, deuterium, hydrogen. Which will have more? Tritium, deuterium, hydrogen. Then we have CT3, CD3, CH3. Which will have more? I think I have explained this concept once in the D block only, if you remember.
Yes, sir.
On what basis I have explained that CT3, CD3, CH3 will be having greater effect? Anyone remember? Can just say it out. Yes, Faizan, which will have greater electron donation tendency? CT3, CD3, CH3.
So CD3 because of effective resonance.
CD3 because of effective resonance.
Like you have explained acidity at that time. I
Yeah,
think
acidity
will
at that
be
time.
yes, sir.
So why? What is the reason because of why CT is greater than CD than CH? So bond length order is CH bond greater than CD bond than CT bond. Bond length order. Why it is so? Okay, I'll explain again. Listen carefully. Okay. So whenever we have like Bohr's theory you studied, right? So there we have explained the same logics again. So Bohr's theory, what are the equations we have? Like we have nucleus at the center. Whenever you have nucleus at the center, electrons are going to be revolving in different orbits, stationary orbits. The electron which is revolving in a particular orbit will have electrostatic force of attraction with the nucleus, and mv square by r should be is equals to 1 by 4 pi epsilon naught q1 q2. Q1 is the charge of electron and Q2 is the charge of nucleus, that is E into Ze, that is Ze square by R square. And one more equation is MVR is equals to NH by 2 pi. MVR, angular momentum, is an integer multiple of H by 2 pi. From here I can write velocity V is equals to NH by 2 pi mr. Velocity V is equal to NH by 2 pi mr. I can substitute in the first expression. I can write m by r into V square is n square h square by 4 pi square m square r square, that is equals to 1 by 4 pi epsilon naught Z square by r square. So from here I can cancel out r square and write the expression of radius r. R will be, the expression of radius r will be n square h square by 4 pi square. R I am getting right. R I am taking this r to the other sides. N square h square by n square h square into 4 pi epsilon naught divided by 4 pi square. M by m square will be m into z square. Z square. So you have radius of the orbit in which the electron is revolving, that is inversely proportional to mass of electron. Radius of the orbit in which the electron is revolving, that is inversely proportional to mass of electron. These are again useful only for a single electron species. But here what you have to understand carefully is the electron is not actually revolving around a nucleus which is stationary, but the nucleus also has some motion. Nucleus also has some motion, so you have to consider, since the nucleus is not completely stationary, if you think logically, since the nucleus isn't a stationary, so instead of mass of electron, what you have to consider? The radius of the orbit in which the electron is revolving, that should be inversely proportional to reduced mass of the electron. Reduced mass of the electron is equals to mass of electron into mass of nucleus divided by mass of electron plus mass of nucleus. So from this, what I can say, deuterium, tritium, deuterium, hydrogen, I can say reduced mass of electron in the case of tritium is greater because tritium is large in size, large in mass because of more number of protons. When compared to reduced mass of electron in the case of deuterium, that is greater when compared to reduced mass of electron in the case of hydrogen. Reduced mass is inversely proportional to radius. So radius of the orbit in which the electron is revolving in the tritium, that is least when compared to the radius of the orbit in which the electron is revolving in deuterium, then radius of the orbit in which the electron is revolving in hydrogen. So smaller the radius, what we can say, greater is the electron density. So if you think of CT bond, in the CT bond, whatever the electron density is there, that is moving in a smaller radii. In the CD bond, the electron density is moving in a larger radii. In the CH bond, the electron density is moving in a much larger radii. So which bond is stronger? Bond energy, if you try to compare, CT bond is a stronger bond when compared to CD bond. CD bond is a stronger bond when compared to CH bond. So bond energy and bond length, they are going to be different. So also we can say, if CT bond is a stronger bond and more electron density is present in the CT bond, why? Because electron density is moving in a smaller radius. Why? Because from this analysis. So in the CT bond, the electron density is moving in a smaller radius. So electron density near the carbon is greater. So CT3 will be a better electron donating group than CD3, then CH3, because in the CT bond, more electron density is present in a smaller radius. So charge density is high. Everyone understood this or not?
Yes, sir.
Yes.
So same CT3 greater than CD3 greater than CH3. This is a true order in the case of inductive effect where you are trying to compare the electron donation tendency. But if I talk of hyperconjugation, in the case of hyperconjugation, which bond is a weaker bond? CH or CD or CT? CH is a weaker bond. So the CH bond is weaker bond. So CH3 will be involving the hyperconjugation greatly when compared to CD3. Understand that point, because I can also compare the hyperconjugation in the upcoming sessions. Here it is inductive effect. CT3 is a better electron donating group by inductive effect alone. But I can also have CT3 connected to CH2 plus, CH3 connected to CH2 plus. Yes or no? So here, if you look at this alpha carbon, here we have alpha hydrogens and alpha deuteriums. So CT3 means you have CT bonds, 3 carbon deuterium bonds. Here we have 3 CH bonds. This CH electron density has to be broken. What is hyperconjugation? Can anyone say? Can anyone say what is hyperconjugation? The polarization of the adjacent sigma CH electron density to be donated to the vacant p orbital. That is said to be hyperconjugation. Here in the CH2 plus we have vacant p orbital. The alpha CH on the alpha carbon, whatever the hydrogen we have, sp3 hybridized alpha carbon should have alpha hydrogen. In that CH bond, whatever the sigma electrons we have, they can be donated into the vacant p orbital to actually involve this particular CH bond in the hyperconjugation, generating no bond resonating structures. That means if you have CH3 CH2 plus and a CT3 CH2 plus, since the CH bond is a weaker bond, it can have more hyperconjugation when compared to CT3 CH2, because CT bond is stronger bond, so CT bond can't be broken easily, so less hyperconjugation. Understood now? Whenever I am talking about hyperconjugation, there comes the breaking of CH bond. CH bond can be easily broken, so number of hyperconjugated structures in CH3 CH2 can be easily developed, but that cannot be true in case of CT3 CH2 plus. Is that clear?
Yes, sir.
Yes.
Yes, right. Very good. Plus effect showing groups or atoms. So CH2 minus, NH minus, O minus, C double bond O minus, C CH3 CH3 CH3, CH CH3 CH3, CH2 CH3, CT3 CD3 CH3. This is the complete order. This is everything we have studied. CH2 minus, NH minus, O minus. Why it is so? Carbon is less electronegative when compared to nitrogen. Nitrogen is less electronegative when compared to oxygen. So less electronegative atoms can easily donate the electron pairs. C double bond O minus is in resonance, so it will have net electron density donation is decreased. Then you have 3 methyls connected to carbons, 2 methyls connected to CH, 1 methyl connected to CH2. So greater the number of alkyl groups, greater is the electron donation tendency. CH2, CH3, after that CT3, CD3 and CH. This is the complete order of plus I effect of different types of groups which are electron donating groups. Is that clear? So this is a complete effect of plus I effects. Complete order of plus I effect. Right, let us proceed further. Then we have minus I effect. Minus I effect. Minus I effect showing groups or atoms. Minus I effect means electron withdrawing groups. So if carbon is connected to fluorine, chlorine, bromine and iodine, so which can withdraw the electron density greatly?
Fluorine.
Fluorine can withdraw the electron density greatly, then chlorine, then bromine, then iodine. Yes or no?
Yes,
Based on
sir.
electronegativity. Then fluorine OH, C triple bond CH, NH2, C6H6, CH double bond CH2. Here what you will have? F will have greater, then OH, then C triple bond CH. Based on electronegativity, you can compare. The sp hybridized carbon will have more electronegativity when compared to nitrogen. That point you have to remember. sp hybridized carbon will have more electronegativity more electronegativity than nitrogen. Right? And if you proceed with the different other orders, these are all minus I effect groups. NR3 plus NH3 plus OR2 plus OH2 plus OR-OH. Try to compare now. This is a complete order. Okay, this is a complete order of minus I effect groups. OR2 plus greater than OH2 plus greater than NR3 plus NH3 plus NO2 C triple bond N COOH. Then halogens, then OR, OH, C triple bond CH, NH2, CCH6. Compare here, students, NR3 and NH3 plus. Just now in the previous slide, we have seen NR3 and H3. NR3 plus NH3 plus. If you look at the order, which is greater? NR3 plus NH3 plus. OR, OH, OR2, OH2. The same three examples we have given earlier. NR3 plus NH3 plus, OR2 plus OH2 plus, OR, OH. Try to look at the order. NR3 plus greater than NH3 plus. OR2 plus greater than OH2 plus. And OR, OH, if you try to compare, OR greater than OH. Why it is so? Generally speaking, NR3 plus means what? NR3 plus means nitrogen connected to 3 alkyl groups. Nitrogen connected to 3 alkyl groups, and nitrogen is also connected to some other. Nitrogen is also connected to some other carbon-carbon system like CH3, CH2, and nitrogen uses lone pair, so it has a positive charge. So more the positive charge of nitrogen, more is the electron withdrawing tendency or not? Yes or no? If a nitrogen has more positive charge, more it will withdraw the electron density. So if you look at nitrogen connected to alkyl groups, what are these alkyl group? Electron donating or electron withdrawing group? Alkyl group.
Electron donating.
Electron donating group. So 3 alkyl groups are electron donating. So they are electron donating. Consider same type of molecule CH3, CH2, NH3 plus, NH3 plus. 3 hydrogens. They are not electron donating group. Hydrogens are not electron donating group because it is taken as a reference atom. So because of these 3 alkyl groups, electron donation is happening. Because of electron donation, positive charge of nitrogen is decreased. If a positive charge of nitrogen is decreased, it should not withdraw the electron density greatly. So as per this logic, which should be having greater? NR3 and NH3. NH3 should be greater. So is the order correct or incorrect? Or are we missing something else? Order is correct. This is the correct order of electron withdrawing tendency, that is minus I effect showing groups. NR3 plus has greater electron withdrawing tendency when compared to NH3 plus. Why it is so? But if you think of electron donation from the alkyl groups, we are having reduction of positive charge of nitrogen, that is decrease in the positive charge of nitrogen. Because of decrease in the positive charge of nitrogen, the electron withdrawing tendency that has to be decreased. But we are saying NR3 plus withdraws the electron density greatly. Same logic you can apply to OR2 plus also. Same logic can apply to OR2 plus also. CH3, CH2, oxygen possessing positive charge, 1 lone pair and 2 alkyl groups. CH3, CH2, oxygen possessing lone pair and positive charge, 2 OH groups. The reason here is you have to think of number of alkyl groups, and if we have same number of alkyl groups, there the repulsions between the groups will be high. Yes or no? Understand the reason, all of you? Because of, write down that point in the previous slide itself. Okay, in NR3 plus, because of the presence of 3 alkyl groups, the repulsion between the repulsion increases, and because of that the repulsion increases, and because of that bond angle increases or decreases?
Increases.
And bond angle increases. Bond angle increases means what happened to the electronegativity? Bond angle is directly proportional to bond angle is directly proportional to electronegativity, directly proportional to percentage of S character and electronegativity. Therefore, nitrogen in Nr3 plus is more electronegative when compared to nitrogen in NH3 plus. Understood now?
Yes, sir.
Okay, Nr3 plus, if you think of electron donation tendency of alkyl groups, you will get different order. NH3 plus should be greater when compared to Nr3 plus. But nitrogen in Nr3 plus has a different electronegativity when compared to the nitrogen in NH3 plus. The reason is because in Nr3 plus there are 3 alkyl groups. Because of those 3 alkyl groups, the bond angle increased. Because of increase in the bond angle, the percentage of S character, thereby electronegativity, all are going to be increased. I have explained this even in chemical bonding. In chemical bonding, we have seen the bond parameters. In the bond angle, we have discussed the first one is if we have more electronegativity, greater the bond angle, greater will be the percentage of S character, yes or no, and greater will be electronegativity. So nitrogen in Nr3 plus is more electronegative when compared to nitrogen in NH3 plus, and thus Nr3 plus is a better electron withdrawing group when compared to NH3 plus. Now I'll give 3 other groups: Nr3, NH3, all are connected to another species, Nr3 plus, NH3 plus. NHR2, NH2R plus NHR2. In this case, what happens? When you have Nr3 plus, NH3 plus, NH2 or NHR2, only when the 3 alkyl groups are present, then only the bond angle is going to be increased, then only electronegativity concept has to be applied. If you have only 1 alkyl group connected to nitrogen or 2 alkyl groups connected to nitrogen, then the electron donation from the alkyl group will be dominating factor. If electron donation from alkyl group is dominating factor, there that will decrease the positive charge. So in that case, this is going to be the order. Nr3 plus will be having greatest, then you will have NH3 plus, then you will have NH2R, because in NH2R the electron donation is happening from one alkyl group. Bond angle is not the dominating factor now, electron donation is dominating factor. You may ask a question, sir, why not bond angle is dominating factor? Because of the presence of hydrogens. The 3 alkyl groups, whenever they are present, then only the increase in bond angle will be sufficiently dominating factor. If not, this is the order of the dominating factor will be electron donation of alkyl groups. So if here we have one alkyl group, so positive charge is reduced. 2 alkyl groups, positive charge is more reduced. So based on that combined effect, this will be the complete order of minus effect for substituted nitrogens, substitute amines you can say. Nr3 plus greater, then NH3 plus, then NH2R, then NH plus R2. Same logic you can apply and apply that to OR2 plus and OH. OR2 plus and OH plus, OR and OH. Applying the same logic, you will get these orders. Is that clear, students?
Yes.
Yes.
Yes. So this is how the order is obtained. So applications of inductive effect. So stability of cation. So charge increase means stability decrease means. Charge increase means stability will be decreasing. Like if I am neutral, I am not going to be moving towards positively charged species or negatively charged species. If I have some charge, if I have positive charge, then I will be attracted towards negative charge. If I have negative charge, I will be attracted towards positive charge. If I am neutral, I am not going to be attracted by any other charge species. You don't include the concept of gravity here. Okay. All mass bodies, they are going to have gravitational force of attraction. That is a different concept. These are microscopic entities. Gravitational forces you are not considering here. Just based on electron withdrawing tendencies and electron donation tendencies, we are applying the concepts. Stability of cation. If I am having a positive charge and I am connected to some groups, which are withdrawing the electron density from me. I myself has a positive charge and I am connected to some other groups which are withdrawing electron density. So my positive charge will increase or decrease.
Increase.
Increase.
Positive charge increase means stability will be decreasing. Yes or no? So if we have a cation, for that cation, if that cation is connected to electron withdrawing groups means minus I groups. If we have minus I group, what happens? The positive charge of the cation increases. Because of increase in positive charge, stability decreases. So stability is inversely proportional to minus I effect and directly proportional to plus I effect for the cation. For the anion, it would be reverse. Anion stability is directly proportional to minus I effect and inversely proportional to plus I effect. And this is the order. Stability is directly proportional to electronegativity is the dominating factor across the period. Size is the dominating factor down the group. If you are comparing species in a particular period, electronegativity is the dominating factor. If you comparing the species in a particular group, size is the dominating factor. Electronegativity is the dominating factor in a period, size is the dominating factor in a group. Right on that point. Electronegativity is the dominating factor in a period. Size is the dominating factor in a group. Generally, first check electronegativity or size and then compare effects. First you have to check the electronegativity or size and then only you have to compare the effects. Let us start with different cases. As I have told you, dominating factor will be electronegativity. If I am comparing CH3 minus NH2 minus OH minus F minus fluorine is more electronegative. Negative charge or more electronegativity is stable or not? Yes or no?
Yes.
So I am comparing electronegativity, that is dominating factor in a period is electronegativity. Cl minus Br minus I minus, dominating factor is size. So F minus Cl minus Br minus I minus, if I try to compare, I have to talk of sizes. So iodine is much larger in size. So the outermost electrons are least attracted towards the outermost electrons are going to be least attracted. And if you try to compare HF, HCl, HBr, HI, the HI bond that is going to be cleaved easily producing H plus and I minus. HBr will be less, H plus and Br minus. If you try to compare acidic nature, which will be most acidic? HI will be most acidic or not?
Yes.
HI is most acidic, means can I say I minus is more stable?
Yes, sir.
Yes.
Therefore, I minus is more stable. Yes or no? HI is most acidic because I minus is going to be more stable because of least repulsions. If you compare HF, the HF bond is going to be stronger bond. So F minus is going to be less stable when compared to I minus. Like that, whenever I am trying to compare the ions in a respective group, I am comparing sizes. Whenever I am trying to compare the species in a particular period, we have to think about electronegativity. Electronegativity is the dominating factor in the particular period. I am not comparing the electronegativity of fluorine, bromine, and iodine because size is the dominating factor in the group. Okay. First, you have to check electronegativity or size. Then you have to go with the other effects like electron donating groups, electron withdrawing groups, and all. Try to solve this. Compare stability. You have to give the answers for this. Compare stability. CH3, CH3, C minus, CH3, CH minus, CH3, CH3, CH2 minus, CH3 minus.
Sir, A is the least stable.
Yeah, order. What is the order?
A least stable, then continue.
Yes or no? Because in A we have electron donating groups. So C will be because all the three methyl groups are electron donating. Carbon already has negative charge. So negative charge on carbon is increased. Negative charge increased means stability decreased. So A will be least, then B will be least, then C will be least. Yes or no? So D will be the highest. So because in the carbon, these are all carbanion systems. So carbon and carbon is connected to methyl groups. More number of electron donating groups, negative charge is increased. Negative charge increased means stability decreased. So negative charge is less here in the D. So D will be more stable than C, then B, and then A. D, C, B is the right order, right? Try to compare here. CH2, CH2 minus NO2, OH, CH2, CH2 minus, Cl, CH2, CH2 minus, CH3, CH2 minus. NO2 is electron donating or electron withdrawing? NO2, electron withdrawing. I am considering the electron withdrawing groups. Chlorine is also electron withdrawing. All are electron withdrawing by inductive effect. And here we have CH2H. With respect to hydrogen, there is no effect. So NO2, OH, Cl. OH is also electron withdrawing. You should not consider lone pair of electrons on oxygen and electron donation. That is electron donation with respect to resonance or mesomeric. We have, as of now, studying only inductive effect. Ultimately, we have mesomeric effect, hyperconjugation, everything, students. We have to include all of them whenever you are studying the ultimate molecules. Here we have just including inductive effect because there is no possibility of resonance. Is there a possibility of resonance here? No, because conjugate is not present. So NO2, OH, Cl and hydrogen, which is the minus I effect order? NO2 is going to be greater electron withdrawing group, then chlorine will be withdrawing greatly, then OH, then hydrogen. So what is the order now? If we have electron withdrawing group, negative charge is decreased. Negative charge decreased means stability is increased. So A will be having greater stability, then C, then B, and then D. A, C, B, D. Is that clear?
Yes.
Yes.
A, C, B, D. Why we are not considering resonance? Because there is no conjugation system. If we have OH and O2, they are also electron withdrawing or electron donating by resonance, but we should have a conjugation for that. Compare stability now. Fluorine, chlorine, bromine, iodine. This is very simplest case. A, B, C, D have given. What is the order? All are electron withdrawing groups by inductive effect. Which withdraws the electron density greatly? Fluorine, then bromine, then iodine. Fluorine withdraw greatly, then chlorine, then bromine, then iodine. So if you try to look at that point, minus I effect of halogens is fluorine greater than chlorine, then bromine, then iodine. So A, B, C, D, that will be the right order for the stability. More is the electron withdrawing, more is the stability gain. More stability means more stable. Compare stability here. CH2 minus CH2, CH2, CH2Cl, CH2 minus CH2, CHCl, CH3, CH2 minus CCl, CH2, CH3. Distance is changing, everything is same here. The type of group is same, carbon ions are same. Just the distance is changing. So I can say with respect to distance, inductive effect is more dominant when the distance is less. So minus effect of chlorine decreases as the distance from the carbon and carbon increases. So C, here we have more electron withdrawing tendency, then B, and then A because the distance is high. C, B, A, that will be the right order. Is that clear, students?
Yes.
Yes, right. Try to compare here. CH triple bond C minus, CH2 double bond CH minus, CH3 CH2 minus.
A more stable than B
Why?
and C. Because
Why?
carbon is sp hybridized and it will.
Very good. So sp hybridized carbon will have more electronegativity. Negative charge and more electronegative atom is stable. So here carbon is sp hybridized. Here it is sp2 hybridized. Here it is sp3 hybridized. Negative charge on more electronegative atom. More electronegative atom is more stable. Negative charge on more electronegative atom is more stable. So based on that, we can simply compare. CH triple bond C minus is greater than CH2 double bond CH minus, then CH3 single bond CH2 minus. So A, B, C, right? Compare stability here. CH3, CH2, CH2 minus, CH3, CH, NO2, CH3, CH, CN, and CH2 minus. So minus A effect order, if you look at NO2 is a greater or better electron withdrawing group when compared to CN. Stability of carbon increases as minus A effect increases. So B and C, we have electron withdrawing groups. So B greater than C, greater than A, that will be the order of stability. Electron withdrawing groups means removing the electron density. Decreasing the charge means increasing the stability. So based on that, you can write the stability order. So what you have to do is remember the plus I effect order and minus I effect orders. Whatever the order I have given, you have to remember that, so that which group is better electron donating, which group is better electron withdrawing, That idea you'll get. Right, students? So after that, let us proceed with the next two concepts. Acidic strength. How we can understand the acidic strength? What are acids? Acids are those substances which can donate the H plus ions. So acid is something which is donating the H plus ion, and along with that we have conjugate base. Acid more stable, more stronger acid. More stronger acid means more stable conjugate base or not? Understand this point carefully. If acid is more stronger, then the conjugate base should be more stable. More the stability for the conjugate base, more stronger is the acid. Acid is more stronger means Ka is high means higher acidity. Higher acidity. Ka high means higher acidity. Ka high means pK will be low. pK low or Ka high means higher acidity. More stable conjugate means more stronger acid. If the acid is a stronger acid, what about the strength of conjugate base? Strong acid will have weak conjugate base. Weak conjugate base will be having for every strong acid, and if the acid has to be stronger, the conjugate base has to be more stable. Weak conjugate base is more stable. Can I derive these two? Stronger acid means more stable conjugate base. Stronger acid means weaker conjugate base. If I am trying to compare the stability and ability, both, like stability of conjugate base more means it is going to be a weaker conjugate base. Like that also you can compare. So acids are those substances which can donate H plus ion. So Ha gives H plus and A minus. So Ka is the dissociation constant for the acid. Concentration of H plus into concentration of A minus divided by concentration of Ha. Ka is equal to acid dissociation constant. More H plus ions are there means more will be the Ki. Ka more means pK less. So concentration of H plus high means pH will be less. So that will refer to strong acid. Weak acid means everything will be reverse. Concentration of H plus will be less. Ka will be less. pK and pH will be high. That is a weak acid. Acidic strength is directly proportional to stability of conjugate base. Stronger the acid, weaker the conjugate base. So I can say more stable the conjugate base is, weaker will be the respective conjugate base. Acid gives conjugate base upon loss of H plus. HCl gives Cl minus upon loss of H plus. Acidic strength is directly proportional to minus A effect and plus A effect. We'll apply this logic by solving examples. Try to compare acidic strength here. Acidic strength you have to compare just by dissociating the H plus, producing the respective conjugate base, compare the stability of conjugate base. So it will produce what? Upon loss of H plus, it produces CH3 minus. NH2 minus produces what? NH3 produces NH2 minus. H2O produces OH minus. HF produces F minus. CH3 minus, NH2 minus, OH minus, F minus, which is more stable?
F minus.
F minus is more stable because negative charge present on more electronegative atom. I am talking of electronegativity because I am comparing the species which are in the same period. In the period, electronegativity is the dominating factor. So F minus is greater than OH minus, then CH3 minus, then NH2 minus, then CH3 minus. So this is the order of stability. So more stable the conjugate base is more acidic. So CH4 least, then NH3, then H2O, then HF. So acidic strength order is D will be more acidic, then C, then B, then A. Is that clear to everyone?
Yes, sir.
Yes, right. Compare here. Compare acidic strength CH3NH2, CH3OH, CH3SH. Compare acidic strength CH3NH2, CH3OH, CH3.
B greater.
What is the order? Ultimate order?
BCA. BCA.
BCA. Try to think again. So CH3NH2. Upon we have to leave the, you have to remove the H plus. Loss of H plus means what you will get? CH3NH minus. Again, you have to remove H plus. Loss of H plus, you will get CH3O minus. Again, you have to remove loss of H plus, you will get CH3S minus. Compare A and B now first. Why? Because nitrogen and oxygen, they are in the same period. So A and B, if you try to compare, CH3NH minus CH3O minus, negative charge on more electronegative is stable. So comparing A and B, which is stable, more stable? B is more stable than when compared to B is more stable when compared to A. That
A.
means conjugate base of B is more stable, means B is more acidic when compared to A. So B greater than A, that point you can say. Now compare B and C, because oxygen and sulfur, they are in different periods, but they are in the same group. So CH3OH is going to be obtaining loss of OH bond. The cleavage of OH bond will give CH3O minus and H plus. CH3SH will give CH3S minus and H plus. Here the cleavage of SH bond. Which bond can be cleaved easily?
SHC.
SH bond can be cleaved easily because sulfur is very large size atom, hydrogen is small size. So poor is the overlapping, weaker the overlapping, greater the bond cleavage. So this bond can be cleaved easily because of size. Size I am comparing now. So if this bond can be cleaved easily, CH3S minus is more stable or not?
Yes.
So CH3S minus more stable means CH3SH, that should be more acidic when compared to CH3OH. So B greater than A, C greater than B. So I can compare the ultimate order. Therefore, C should be greater then B, then A. CBA will be right order. Got it now, everyone? So whenever we
Yes.
have different species in different periods and different groups compared directly, compare the species in the period first, then compare the species in the group, arrange them in a proper manner. CH3NH2 will give CH3NH minus, CH3OH gives CH3O minus, CH3SH gives CH3S minus. If you try to compare the stability of CH3NS minus, CH3O minus, CH3S minus, C greater than B greater than A, that will be the correct acidic strength order, because CH3O minus and CH3S minus, if you try to compare stability, S minus is more stable because SH bond can be cleaved easily because of large size sulfur atom. Right? Compare here. Compare acidic strength in this case. R C triple bond CH NH3 H2O. This is sp hybridized carbon. This is nitrogen. So loss of H plus will produce R C triple bond C minus. Loss of H plus will produce NH2 minus. Loss of H plus will produce OH minus. H2O produces OH minus, NH3 produces NH2 minus, RC triple bond CH produces RC triple bond C minus. So negative charge of more electronegative is stable, which is most electronegative oxygen, then carbon, sp hybridized carbon, then nitrogen. So C should be greater than A and then B. This is the order of stability of respect to conjugate bases. So that will be the same order of acidic strength. Acidic strength is directly proportional to stability of conjugate base. So directly proportional to electronegativity. So C greater than B, A greater than B, that will be the right order. Compare here. CH3OH, CH3CH2OH, methanol, primary alcohol, secondary alcohol, and tertiary alcohol. Methyl alcohol, primary alcohol, secondary alcohol, tertiary alcohol, acidic strength. Which alcohol is more acidic? How to compare, students? Give answer for this question. All of you try to do the comparison and give the answer for this question. Simple.
Sir, A is correct.
Why?
Sir, in the tertiary carbon, once it loses hydrogen, it has more oxygen has more electron density.
Yes. So ultimately, you can just compare the, whenever they're asking acidic strength, you have to respect to produce conjugate base, look at the stability. So here we have CH3O minus, here we have CH3, CH2O minus. Here we have CH3, C, CH3, CHO minus. Here we have CH3, C, CH3, CH3O minus. Methyl groups are electron donating groups. So more number of electron donating groups, more is the electron donation. So electron donation grade means the negative charge on oxygen is already there and we are donating electrons. So repulsions will be increased. So A, there is no electron donation because no methyl groups, only CH3O minus. CH3, CH2O minus, CH3, CH, CH3O minus, CH3, C, CH3, CH3O minus. In all these cases, electron donation is increasing, because of increased electron density, stability is decreasing. So A will be greater, then B, then C, and then D. Okay, CH3OH. Respect to conjugate base stability, I am comparing. So A, B, C, D will be the right order because we are more electron donation. Already negative charge is there in oxygen. We are giving electrons means stability will be decreased, right? Because of repulsions. So like that, you can say A greater than, B greater than, C greater than D. That is the right order. That is the right order of acidic strength. More number of alkyl groups, more plus effect. Acidic strength directly proportional to stability of conjugate base. So acidic strength is A greater than, B greater than, C greater than D. Is that clear, students? Everything so far?
Yes, sir.
Yes, this is all inductive effect only. We have not included hyperconjugation or resonance as of now. Then basic strength. Basic strength means base is a species which can share lone pair of electrons to H plus. Basic strength is directly proportional to Kb. Like Ka is directly proportional to acidic strength. Kb is directly proportional to basic strength. More is the value of Kb, more is the basic strength. More is the value of Kb, less will be the pKb. Kb and pKb, they are inversely proportional. So higher the basic strength, more stable the respective conjugate acid is. So basic strength is also directly proportional to stability of conjugate acid. It is again directly proportional to ability to donate H plus, ability to donate electrons. Like ammonia, we have lone pair of electrons and nitrogen. If they can be easily donated, so it is going to be a stronger base. And it is inversely proportional to electronegativity and directly proportional to plus I effect or minus I effect. That means if you try to increase the electron density on nitrogen, more electron density on nitrogen, more is the donation. So more number of plus I groups, more electron density, more will be the basic strength. If you have electron withdrawing groups, electron density is decreased. If electron density is decreased, obviously what happens? If electron density is going to be reduced, you will be having less electron density, so less is the donation, so less will be the basic strength. So NH2 connected to electron withdrawing group, electron density is decreasing. Electron density is going to be decreasing because electron withdrawing group withdraws the electron density from nitrogen. Electron density decreasing means ability to donate that will decrease. So basic strength decreases. NH2 connected to electron donating group arrow will be reverse. Electron donating group will increase the electron density on nitrogen. So ability to donate increases. If ability to donate increases, basic strength will increase. Basic strength will be increasing in the case of NH2 connected to electron donating group. Basic strength will be decreasing in the case of NH2 connected to electron withdrawing group. Is that clear, students? Is everything clear so far?
Yes.
Yes, sir.
Yes.
Yes, right. Compare basic strength CH3, CH2, NH2, CH3, CH double bond NH, CH3, C triple bond N.
A, B, C.
Because it is sp3 hybridized nitrogen, it is sp2 hybridized nitrogen, it is sp hybridized nitrogen. Lone pair of electrons are present on nitrogen. sp hybridized nitrogen will have more electronegativity, so it will withhold the electron density on nitrogen. So electron negativity of nitrogen high means it will withhold the electron density on nitrogen only. It will not allow the lone pair to be donated easily. So A will have more tendency to donate, then B, then C. Yes or no? sp3 hybridized nitrogen, sp2 and sp hybridized. Basic strength is directly proportional, inversely proportional to electronegativity. So A will be more basic, then B, then C. Compare here. CH3, CH2, NH2, CH3, NH2, CH3OH. Compare here, all of you. Compare basic strength.
Let's see.
So lone pair of electrons on nitrogen is there. We have CH3NH2 and CH3CH2 means here electron donation is there. So when you try to compare A and B, A will be greater when compared to B. Why? Because electron donating group is present in A, which is increasing the electron density on nitrogen, thereby increasing the attack. More electron density means more is the possible attack. CH3OH and CH3NH2. Lone pair of electron present on nitrogen. Nitrogen is less electron negative when compared to oxygen. Oxygen is more electron negative, so oxygen will not donate the lone pair easily. So when compared to B and C, C will be having least basic nature because it is more electronegative oxygen. So A greater than B greater than C, that is the right order. Is that clear?
Yes.
So basic strength is inversely proportional to electronegativity. That is directly proportional to plus effect. Applying that logic, we will get A greater than B greater than C. Compare basic strength in this species. Cl, CH2, CH2, NH2, NO2, CH2, CH2, NH2, NH3 plus CH2, CH2, NH2. NH3 plus is electron withdrawing group. NO2 is also electron withdrawing group. Chlorine is also electron withdrawing group. But what is the order? Which is a stronger electron withdrawing group? NH3 plus is a stronger electron withdrawing group. Then NO2, then Cl. So more is the electron withdrawing tendency. Least is the basic nature. So NH3 withdraws the electron density greatly. So nitrogen has lost most of the electron density in C. So C is going to be the least basic. So A will be great, more base, then C, and then A, then B, then C, because Cl withdraws less electron density. So more electron density is present on nitrogen in compound A. A, B, C, that will be the right order. Basic strength order is A, B, C. Basic strength of primary, secondary, and tertiary amine. How to compare this basic strength? Amines, primary amine, secondary amine, tertiary amine. How to compare basic strength? In a gas phase or non-polar solvent phase, if you look at the basic strength, more number of alkyl groups means more is the electron donation. If more is the electron donation, the electron density on nitrogen will be increased greatly. If more is the electron density on nitrogen, that will be a stronger base. So in a gas phase or non-polar solvents, you can say lone pair of electrons on nitrogen. The electron density on nitrogen is more in tertiary amine, then secondary, then primary, then ammonia. So this will be the right order. Yes or no? In a gas phase or non-polar solvent phase, just we have to think of electron donation tendency from the alkyl groups. More number of alkyl groups, more is the electron donation tendency. If more is the electron donation tendency, more electron density on nitrogen, more is the electron density on nitrogen, more can be the donation. So more basic nature. But in most of the cases, we have amines, primary, secondary, tertiary amines in the polar solvents. So in the polar solvent or in the aqueous phase, we have to consider three factors. In aqueous phase, following three factors we have to consider. One is the inductive effect. Inductive effect means, based on inductive effect, we can say tertiary amines greater than secondary, then primary, then ammonia. Other is the solvation, and the other is the stability of conjugate. Other is the solvation, and the other is the steric hindrance. We will understand what is solvation and steric hindrance now. Like how ammonia, if you take ammonia, lone pair of electrons are there in ammonia. They were attacking H plus ions. If lone pair of electrons on nitrogen, if it attacks H plus ions, it forms NH4 plus. So if it NH3 is a base, NH4 plus is a conjugate acid. NH4 plus is a conjugate acid. Can I again say more stable the conjugate acid, stronger is the base? Like in the acid, what we have said? More stable the conjugate base, more stronger the acid. In the base, I am saying for every base will have a conjugate acid. More stable the conjugate acid, more stronger the base will be. More stronger the base will be. Now we look at the different solvations happening. Like if we have a tertiary amine, lone pair of electrons on nitrogen attack H plus. This hydrogen can develop hydrogen bonding with the H2O molecule because hydrogen has partial positive charge, partial negative charge present on oxygen from the H2O. Like in the conjugate acid of tertiary amine, how many hydrogen bonding sites are there? In the conjugate, this is a conjugate acid. Like if you have a tertiary amine, R3N is a tertiary amine, we have lone pair of electrons on nitrogen. It is attacking the H plus ion. As soon as it attacks, will form R3NH. Nitrogen uses lone pair to form the new NH bond. So electron density on nitrogen has been decreased. So nitrogen has a positive charge. So R3NH with a positive charge on nitrogen. Because of the presence of positive charge on nitrogen, this NH electron density will be moving, developing partial positive on hydrogen. Because of partial positive charge on hydrogen, it will develop a hydrogen bonding with the partial negatively charged oxygen. How many hydrogen bonding sites are there? With the, this is a conjugate acid of tertiary amine. In the conjugate acid of tertiary amine, how many hydrogen bonding sites are there? Only one site or not? One hydrogen bonding site. Similarly, if you consider secondary amine, how many hydrogen bonding sites will be there?
2.
Two hydrogen bonding sites. Tertiary amine, secondary amine, primary amine, if you consider, you will have 3 hydrogen bonding sites. If you consider quaternary, just ammonia, if you consider ammonia, you will have 4 hydrogen bonding sites. So look at the stability of the conjugate acid. Which conjugate acid will be more stable? Which has more number of hydrogen bonding sites? Which has more number of hydrogen bonding sites?
Ammonia.
Ammonia. So according to the concept of solvation, what should be the order? Ammonia should be most basic, then primary amine, then secondary, then tertiary. So more solvation, more stable conjugate acid, more strong base. So this is the order based on solvation only, based on solvation alone. Reverse 3 degree greater than 2 degree greater than 1 degree greater than ammonia. This is based on inductive effect alone. Let's say effect alone. And we have steric repulsions also, because if the alkyl group R is much larger, then you cannot have hydrogen bonding greatly. Third effect is steric hindrance. Due to steric hindrance, solvation decreases or not? Because if the R group is bulky group, if the R group is ethyl, then we have different solvation. If it is methyl, we have different solvation. So if due to steric hindrance, the solvation decreases. So the ultimate order of steric hindrance, solvation, and electron donation tendency, combining 3 effects. If alkyl group is methyl group, then secondary amines are more basic, then primary, then tertiary, then ammonia. If alkyl groups are ethyl groups, then secondary greater, then tertiary, then primary, then ammonia. This is the order given by the combination of all these 3 effects. Okay. This is based on the combined effect of solvation plus psi effect and steric hindrance. And if they have not mentioned anything in the question, simply asking what is the order of basic nature for amines, then you have to take it as a aqueous phase only, because most of the reactions are performed in the aqueous medium. That's what I'm saying. If nothing is mentioned, then consider aqueous phase and then mention the order. Is that clear, students? Is everything clear so far?
Yes, sir.
Yes, sir.
Yes, right. So these are the concepts where inductive effect can be applicable, and we can apply inductive effect and decide acidic nature, basic nature, and all other properties. Then we have resonance. Resonance is the other electronic effect. We have not included resonance as of now. What is resonance? When one structure cannot explain all the properties of the molecule, then we are going to write many structures. All those structures are said to be resonating structures. For benzene, we'll write these 2 structures. When a single structure cannot explain the complete properties of a molecule or an ion, then we write different structures. These are nothing but resonating structures. Resonating structures of benzene. Resonating structures of benzene, where the resonance hybrid will be written in this fashion. This is a resonance hybrid. Yes or no? When all the properties of a molecular ion cannot be explained by a single structure, and to explain its properties, more than one structure if it is required, then the molecular ion is said to have resonance. The different structures are called resonating structures or canonical forms. So same examples, benzene, if you try to give the representation of benzene, we have these two structures. These are nothing but resonating structures. And this is nothing but your resonance hybrid. This is nothing but your resonance hybrid. Resonating structures are completely imaginary structures. And what do we have? The real structure is the resonance hybrid. Yes or no? So if you try to write down understand some points. Resonating structures are completely hypothetical or imaginary. The real structure is known as resonance hybrid. The real structure is known as resonance hybrid. The two resonating structures of benzene are equivalent, and equivalent resonating structures have equal contribution to resonance hybrid. That means this structure will be contributing 50%. This is also contributing 50% to the resonance hybrid. What is resonance hybrid? This one. In this resonance hybrid, 50% contribution will be this one, and the other 50% will be this one. Why? Because they are equivalent resonating structures. If we have non-equivalent resonating structures, there will be having unequal contribution. That means among the resonating structures, among different resonating structures also, we can actually compare the stabilities. The stabilities of resonating structures we will also discuss in the upcoming slides. Right, students? So few more points. Resonance involves delocalization of pi electrons. All the resonating structures must have same number of electrons. Electrons are not going to be less in any of the resonating structure. The total number of electrons in two resonating structures should be same. We cannot remove the electrons, we cannot add the electrons. Resonance involves delocalization. The electrons can be delocalized, they can be under motion, not present in a particular position or a particular location. They can be delocalized. All resonating structures must be a valid Lewis dot structure. Every resonating structure will be having a valid Lewis dot structure. Is that point clear? And for resonance, you should have conjugation. For resonance, you should always have conjugation system. Like if you look at orbital diagram of benzene, if you consider benzene which is C6H6, we have p orbitals present in this fashion. In the other resonating structure, we have p orbitals present like this. The overlapping of p orbitals in the resonance hybrid will be shown in this fashion. That means here, whenever we have a double bond between these two carbons, these two p orbitals are overlapped. Double bond here means these two overlapped. Double bond here means these two overlapped. In the other structure, these two overlapped, and these two overlapped. We can also think of the question, or you can ask a question like, sir, if this overlapping is already there, then what is giving the energy to break this overlapping and developing a new interaction? Like if you try to understand the resonance in the orbital diagram picture more, look at this. So this is one overlapping. These are other overlapping possible. And this is your resonance hybrid. If one overlapping is already there, why can't the other overlapping can be developed? Why the other overlapping is developed? Because whatever the overlapping present here, that is not strong overlapping. It is not forming a sigma bond. It is just a pi bond. The pi overlapping is sideways overlapping. It is weaker. So electron density is not completely involved in the overlapping. There is still, although this overlapping is happened, there is lot of electron density which is not involving in the overlapping. Here also a lot of electron density which is not involving overlapping. So that electron density can also have a tendency to overlap to form a pi bond. So that is why resonating structures can have the delocalization of pi electrons. Is that clear? Is that clear,
Yes,
students, everyone?
Yes.
Yes. So we'll stop it here. Next class we'll be continuing with the different delocalizations. Like pi electrons can be in delocalization with positive charge, pi negative, pi, lone pair positive, lone pair negative, all those we'll study. And after that we can look at hyperconjugation, then lot of examples. Fine. Thank you all, everyone.
Thank you,
Thank you,
sir.
sir.
Thank you,
Thank you,
sir.
sir.
Thank you, sir.
Thank you, sir.